Okay, I'm happy to invite Patrick Cote, usually known as Pat, uh, to the UV Club. Pat received his PhD degree in 1994 from McMaster University in Canada. He was a Sherman Fairchild Fellow, just like Ilaria is now at Caltech at the end of the last century, if I can put it that way, 97 to 2000. He then worked as a professor at Rutgers before returning to Canada, where he's now the principal research officer at the Herzberg Institute of Astrophysics. Pat's primary interests include dark matter, galaxy evolution, supermassive black holes. He was the principal investigator of the, rather very well-known Hubble program called ACS Virgo Cluster Survey, ACS Virgo for short. And this program is now being continued with CFH. In fact, I was just talking to Pat about, and almost wrapping up with 40 papers, pretty impressive, as a follow-up with the CFH telescope. Pat is the lead scientist for two large projects. I don't know how he finds the time to be lead scientist for two large ones, but the first one is CASTOR. That's a program project, space project that he'll be discussing. And the second one is an equally big project. It is the next generation Canada-France Hawaii telescope. Basically increasing the size, doubling the size, tripling the size maybe, and equipping with a really very powerful, massively multiplex spectrograph. Okay, Pat, all yours.
Okay, thanks very much, Sri. Thanks for the opportunity. I will correct one thing. So I was the lead scientist for the NG-CFHT project, now known as the Mauna Kea Spectroscopic Explorer, but not since 2013. I'm now just a member of the science team.
I see.
Indeed, it was too much. So
yes,
I'm now focusing on the CASTOR project in terms of actual facilities. So yes, thanks very much for the opportunity to speak today. Good morning, evening, or afternoon to everyone, depending on where you are. So what I will like to do in the next hour or so is basically give you an update of CASTOR and hopefully familiarize you with the project. So I'll start with a bit of the context of the mission, give you a bit of historical background on the development history, how it's gotten to this stage, tell you a bit about the partnerships and the collaborations that are underway, give you an update on how the telescope is designed, try and circle back to the mission context and give you an update on the capabilities and why it's a different mission, unique to the other missions that are upcoming for wide field imaging. Tell you a little bit about the science plan, some of the surveys, tell you about some work that's underway now, and perhaps, since this is organized by Caltech, put a little bit of a US slant onto this in terms of how CASTOR may fit into the US in particular. I realize there are other international participants here. Okay, so start at a very general level, and I'd like to begin by saying, just explaining the international astronomy landscape that we can expect in the next decade. Of course, as I said, this is a very low level. Everybody on this Zoom call understands this, of course, but we're on the threshold of a new era in wide field imaging in astronomy. And there are a number of large, potentially revolutionary projects underway. I'll start with just three very large ones. And of course, we'll start with LSST, now the Vera C. Rubin Observatory. So this is a ground-based wide field telescope, equivalent aperture of 6.7 meters. I believe the commissioning is now estimated to be 2023. I could be a little bit off on that. But the plan for this facility is a 10-year survey covering roughly half the sky in imaging, and it's going to be working in the optical and say, red optical, the visible and the red optical wavelengths. So this is going to be quite the tour de force. That's a ground-based facility, of course. It's going in Chile. And in the north, we have in space astronomy, we have a couple of very important missions upcoming. Euclid, which is an ESA mission. I think the nominal launch date is still late next year. There may be a bit of slippage there, but it's imminent. This is planned to be a 6-year mission and covering about 15,000 square degrees in the so-called Euclid wide survey. And this is going to be red visible and infrared imaging and some slitless spectroscopy as well. And then finally, of the so-called big three, we have WFIRST, now known as the Roman Space Telescope, which is going to be a Hubble-sized facility launching later in the decade, perhaps around 2026. Another mission of a 6-year lifetime. And I said here, sky coverage 2,200 square degrees. That's for one of its major surveys. There are a number of major surveys, but in terms of wide field imaging, there's a 2,200 square degree survey area called the High Latitude Survey. So this will be imaging in the red visible and infrared, very deep imaging. So deeper than Euclid, but over considerably smaller area. So this sort of sets the background. There's quite a lot of things happening in terms of wide field imaging on the ground and in space. And so this sort of leads us into CASTOR and ultraviolet imaging. Of course, we know that it's important as astronomers, we need to observe at multiple wavelengths. This is absolutely crucial to get an understanding of any astrophysical source, or very nearly any astrophysical source. And I'm illustrating this here just with the pictures of the Andromeda galaxy, which we know and love, from radio wavelengths all the way out to X-rays. And of course, you're looking at very different phenomena and sources depending on the wavelength range, from cool atomic gas to warm gas and dust, to normal stars, to hot and massive stars, and to non-thermal sources. Now, in terms of the blue visible and ultraviolet region, this is a very rich area for many different types of scientific study. I've just pulled this list from the excellent webpage of Bob O'Connell, and just to list you some of the research areas that are very critical for ultraviolet. Now, CASTOR isn't specifically an ultraviolet mission. It's sort of the short wavelength region of the optical bands and the ultraviolet as well. I'll come to that in a moment. But my point here is that it's important to have panchromatic coverage of sources in general, and this particular region is rich in terms of diagnostics for astronomy. Okay, sorry about that. Move forward. Right, so of course, why put telescopes in space? CASTOR is a space telescope. I think we know this. We have a number of windows from the ground, most famously the visible and the radio, but it's also possible to work in the millimeter and the infrared. But as I'll come to in a moment, for a number of these wavelength regions, it's better to be in space in any event. So for the ultraviolet region, it's absolutely crucial, of course, because the atmosphere is opaque, mainly due to ozone and molecular oxygen. So absorption and scattering in the atmosphere makes it impossible to do UV astronomy from the ground. But one of the points I'd like to make is that this atmospheric turbulence has an effect on image quality at multiple wavelengths, including in the visible region. So if you see in this comparison between a Subaru ground-based image and a Hubble image of the same source, it's obvious, as we know, that you're better off from space because of the improved seeing. We don't have to contend with turbulent mixing in the Earth's atmosphere. And in fact, for this short wavelength part of the visible spectrum and in the ultraviolet, there are other advantages as well. And one being that you don't have to contend with the background is quite low. And this can be a problem observing at the short wavelength regions of the optical, where we have to contend with a bright moon on a regular basis, but the sky is very dark at these wavelengths in space. And so you sometimes see astronomers refer to as the UV optical infrared region. So there's multiple definitions from this. So if you take it from the Lyman limit up to about 5 microns, 5 microns is a good upper cutoff just because that's where ground-based observations in the infrared region become very difficult. This is a critical region in astronomy, of course, as you can see here in this series of spectral energy distributions for various galaxies. You see this sort of famous double pumped nature here, where at shorter wavelengths you're dominating by emission from stars, and at longer wavelengths you're dominated by emission from dust. But if you focus in on just the optical infrared region, which I've shown here in sort of the pink color, it's this region here to the left of the diagram, so the left half of this short wavelengths. And CASTOR in this region is basically filling in sort of the short wavelength half of this UV optical infrared region. And one of the arguments I would like to make for this particular mission is that for UV astronomy in general, in the era coming up, it's important if you want to build a complete picture of astrophysical sources that you need this short wavelength coverage in addition to the infrared coverage, which will be coming from many different facilities. Okay, so just to belabor the point that in terms of where CASTOR fits compared to other telescopes, it's basically a complement to other telescopes that are coming up like Euclid, Roman, and Ruhmen. Okay, so a little bit about the development history of the mission. As you probably know, Canada, like most other countries, its astronomy community engages in a sort of planning exercises once per decade or so. So in Canada, we have the process called the Long Range Plan for Canadian Astronomy, or the LRP. This is akin to the ASTRO programs in the United States, the decadal reports. So we've done these 3 of these now in 2000, 2010, and 2020. And it's basically a planning exercise for the community, featuring, of course, recommendations on facilities, both on the ground and in space. So if you go back to the 2010 Long Range Plan, the highest priority in space astronomy identified at that time by the community was involvement in one of the next generation of dark energy missions, either Euclid, W first, now known as Roman, or a Canadian-led mission, just given the name Canadian Space Telescope, that would not sort of compete with these projects, but add value to them in some clever way if it could be thought of. So now, as it turns out, Canada attempted to join the Roman project, but it just didn't work out for various reasons. And we are a subset of Canadians, about 25 Canadians are involved in the Euclid mission, but not through a hardware contribution, so not directly to the Euclid mission, but mainly through the ground segment. So a large program mounted on the Canada-France-Hawaii telescope is providing some short wavelength imaging from the ground that's valuable for Euclid science. So the Canadian Space Telescope concept, that's what's known as CASTOR. That's what I'll be talking about. So the idea here, of course, is it's to complement these other wide field imaging facilities. And one way that I like to think of it is it's providing a sort of imaging successor to the Hubble Space Telescope, at least at the short wavelengths. So over the last 10 years or so, quite a lot of effort has been invested in this concept. It began with a concept study back in 2011 and 12 to sort of flesh out the basic idea of a wide field imaging telescope at short wavelengths. There were a number of technical risk items identified in that study, although the science looked quite promising. And so then CSA, the space agency in Canada, funded a number of technology studies that were intended to reduce technical risk with the mission. Lots of them focused on focal plane technologies and detectors, because this is a critical part of the mission, of course. These studies culminated in 2019 with a major new study to basically mature the science. So it had been some time since the science was updated. And so we did that over a 15-month study in 2018 and 19. And we did that with the participation of the respective partners in India, JPL, and the UK. And in 2020, the most recent long-range plan was released. And the top recommendation in space astronomy was CASTOR, which was quite gratifying to see. So this is quite good. Of course, we'd prefer to move faster than this, but these things take time. Space astronomy missions take time. And so this was an endorsement and quite gratifying to see that I think we have an interesting mission. Okay, moving ahead. So a little bit about the team. I mentioned that in 2018 and 19, there was a fairly large study done that updated the mission design and freshened the science case, so to speak. And so that consortium that was involved in this is basically on the Canadian side, it's a partnership between industry, government, and the universities. So I work at the National Research Council, which is essentially responsible for ground-based telescopes, and the Canadian Space Agency, which is responsible for space astronomy. Both agencies have been participating in this work. On the industrial side, the three major partners are Honeywell Aerospace, ABB, and Magellan Aerospace. So these are three of the four largest aerospace companies in Canada, and responsible for quite a lot of space astronomy projects and other astronomy projects over the years. As I said, it's a network of Canadian universities, about 20 or so participating. And we've also been working with international partners, JPL, India, and a consortium in the UK. So we formed some science working groups. I'll give you an update on some of the science plans from these various working groups, but I've just repeated them here for convenience in case that's of interest to people. Okay, so moving along, the technical design. So CASTOR is essentially, it's a wide field imaging telescope, first and foremost. It uses a 1 meter primary mirror made out of light-weighted Zirider. It's an off-axis design, which is useful for a number of reasons. We're baselining this to be a 5-year mission, but the goal is to have a 10-year lifetime, because we believe that there's quite a lot of science to be done beyond the 5-year lifetime. The plan is to put this into a low Earth orbit, dusk-dawn orbit, at an altitude of 800 kilometers. As I said, it's primarily a wide field imaging mission. And in this talk, I'll focus on the wide field imaging, but there are other observing modes, capabilities under consideration and being developed. So there's a slitless spectroscopic mode, which we give, uses a grism to give slitless low resolution spectra in the UV, in near UV channels. I'll say more about this. And there's also a possibility of a multi-slit, two-dimensional small field UV spectroscopy in the UV region over a small field in a parallel field as well. There's also a precision photometer mode, where a single chip is used with a transmissive diffuser plate to produce a fat PSF on a single chip to do precision photometry, which could be useful for exoplanet science. But as I said, primarily, first and foremost, CASTOR is a wide field imaging mission. And so I'll spend most of the talk on that capability. And here are the specs for the wide field imaging as of the 2019 study. As I'll come to, this is all being revisited with some ongoing studies at the moment. But the field of view is about 1/4 of a square degree. The specification on image quality is to have a full width half max of 0.15 arc seconds in all 3 of its photometric channels, and the photometric channels are listed right below that. So we have 3 bands, a UV band, which runs from 150 to 300 nanometers, something like a ground-based U band, not exactly, but something like that, which runs from 300 to 400 nanometers, and then a G band from 400 to 550 nanometers. And the G-band is very similar to the G-band that you would see on a number of ground-based telescopes. So the way the telescope operates, as I said, it's in a low Earth orbit, a polar terminator orbit. So the telescope is always pointed roughly in the anti-sun direction. And so it's, as the Earth moves around the sun, different regions of the sky are accessible at different times. I'll come to that again in more detail in a moment. So the telescope design, let's say a little bit about this. So you can see here, there's an optical diagram, a ray diagram showing we have light coming in down the telescope tube, hits the primary mirror, which is an off-axis mirror, as I mentioned. It's a secondary and a tertiary mirror, and then hits an FSM, or a fine steering mirror, which compensates for the telescope drift and jitter. This is critical in getting the image quality spec that we need. So from the FSM, the light is directed onwards to dichroics and fold mirrors, which separate the light into three different wavelength regions. So there's a G band, the near UV band, and a U band, as I mentioned a moment ago. And so one thing you'll note is you don't see a filter wheel here. And that's because part of the spirit of the design was to keep things fairly low risk and fairly somewhat cost effective. And so we don't have a filter wheel that we can rotate and switch things in and out. The passband definition is done entirely with the optics and the coatings and the detectors. So in this scheme, each of these focal planes here is paved with detectors, CMOS detectors, each about 300 million pixels, so about almost a billion pixels in total. And the passband definition, as I said, is defined. You can see the passband curves up here in the upper right corner. This defines the near UV, U, and the G bands. Okay, so this is a view of the telescope and the bus. So if you look at the upper left figure here, you can see here is the telescope supported on struts. Struts attached to the telescope satellite bus. This is a small Sat 200 satellite bus from Magellan Aerospace. This has got quite good heritage. This is flown on a number of missions, including the recently launched RadarSat Constellation mission, but it's been in use for several decades. So on the bus, you see deployable solar arrays. There's two of those, plus there's one that's not deployable, but permanently mounted on the back of the spacecraft bus. And so upon launch, these solar arrays are deployed. And then we have three solar arrays that provide spacecraft power. You can see the actual telescope is here. The focal plane array compartments sit below the telescope. And you can see here's the design looking down the telescope tube. So this whole thing is about 4.5 meters long and a little over 1,000 kilograms. So think of like a small car, essentially. So it's quite a small thing. And this animation here is still from an animation showing the light coming down this telescope tube and being separated into its different channels here. So currently, we're planning on a launch with the Indian PSLV, Polar Satellite Launch Vehicle rocket. This is an ISRO rocket with good heritage, a very good track record. As I mentioned, the spacecraft weighs a little over 1,000 kilograms, and we're launching into a low Earth orbit. We're expecting a requirement is a 5-year lifetime. The goal is 10 years. And if all goes well, we could launch in 2027. You can see it's a bit of a snug fit, but CASTOR does fit inside the shroud of the PSLV rocket. And as I said, this is a rocket with good heritage, and it's been used to launch, among other payloads, AstroSat, which was India's first astronomy satellite, which included a UV instrument that was a collaboration with Canada. So this was launched in 2015, and that satellite is continuing to work and do interesting science. So as I said, in this particular orbit, this telescope is pointed in the anti-sun direction for most of the time. So by pointing in that direction, of course, you avoid the sun and you provide power to the spacecraft. And so depending on where you're looking in the sky, the illumination of the solar panels will change. And so this is just a plot to show across the sky how much power is being supplied to the spacecraft. So the moment the requirement on the spacecraft power is less than 600 watts. So we have good power generation across the sky. There are a few regions where there's lower power, of course. If you point out of the ecliptic plane in this configuration, this type of orbit, and the geometry of the solar panels, there's less power. So you're power negative at that point, but you can run on batteries and still, if you, for instance, want to access the south ecliptic pole, you can do that for periods of time before you have to return to a lower ecliptic latitude and regain solar power. And on this plot, we've indicated a number of regions of the sky with major surveys, just because those are regions that would be a high priority typically for CASTOR observing programs. Okay, I wanted to say a few words before going in. Yeah.
On the previous slide, what is, you had, yeah, what is the distinction of this plus 10? Is it some LSST limit?
Which?
The color changes at 10 degrees deck. 10 degrees declination above that.
Oh, here, yes, that's an LSST limit.
Okay.
Yeah. Okay, so before launching into the science case and detailed programs, I wanted to pause for a bit and just talk about, the capabilities and the uniqueness of the spacecraft. So, as I mentioned, we have a number of infrared facilities in space, which are going to begin operation this decade. Roman, Euclid, and I haven't mentioned it yet, but JWST, of course, which is focused on the near infrared and also the mid infrared. So these are CASTOR's 3 bands, and so the idea is it fills out the coverage in this UV optical infrared region. As I mentioned, we have the wide field imaging capability, and also the spectroscopy and the precision photometry. Now, comparing to Hubble, so Hubble has been it's a legendary instrument, and so but it will of course not last forever. And so you can't do everything with a 1 meter class telescope as a replacement to Hubble, but you can do a few things very well, and in fact better. And CASTOR for wide field imaging actually outperforms Hubble by quite a margin. So this is a comparison of CASTOR and Hubble discovery efficiencies. This is one particular metric. It's the one that Space Telescope often uses. So as a plot of wavelength here in microns, the vertical axis is this discovery efficiency metric, which I'm taking to be the total system throughput multiplied by the field of view. And you can see these curves over here in the middle and in the right-hand part of the plot. These are various Hubble instruments with 3 ACS, with PIC2, NICMOS, etc. And you can see CASTOR up here enjoying a big advantage compared to Hubble. So why is that? Well, of course, Hubble is the larger telescope. It's a 2.4 meter compared to a 1 meter telescope. So it has an advantage there. But there have been significant improvements in detector and coding technologies since the time of Hubble. And so that gives, in terms of overall throughput, we recoup about half of that from that alone. And then, of course, you have the tremendous gain in the field of view. 1/4 of a square degree. It's a huge advantage. And CASTOR, of course, is operating, because it's using dichroics, it's doing 3 bands simultaneously. So in terms of short wavelength imaging, which I think is the real missing capability in the future, if Hubble ceases to operate, then CASTOR would fill that niche quite well, I believe. Okay, so I mentioned the science maturation study that we did in 2019, and that we had formed science working groups. I've listed them here on the lower right part of the diagram, everything from cosmology to the solar system. And one of the exercises that we did was we asked the science working groups, okay, given these telescopes specifications, of course, there was some back and forth here, there was some iteration, but given the CASTOR specifications and lifetime, what are the legacy surveys that you would like to perform for your particular working group? And while you're at it, what do you believe is the proper mixture of survey and guest observer or geo time? And so this is going to be revisited in an upcoming phase 0, which is scheduled to start in a couple of months, actually. But at the moment, we're thinking something like 70% of the time dedicated to surveys and roughly 30% dedicated to geo programs is probably a reasonable mix. What those surveys are still have to be decided, and this is something that we expect to do with input from our prospective partners. We had a number of surveys identified, candidate surveys, and we did ask the science working groups another question, and that is, can you work together to form one survey, which we call the primary survey, that addresses your key science goals in the context of that single survey? And so we came up with one, which we called the primary survey, which is, in a way, it's kind of a no-brainer. And that is CASTOR imaging of the overlap region between the Rubin telescope, the Euclid Wide Telescope, and the Roman High Latitude Survey, which happens to fall in that region. So this is a region of 7,700 square degrees. Of course, the High Latitude Survey is a subset of that, a little more than a third of that. But this region will have very rich, deep imaging in the optical and infrared. And of course, the value from adding short wavelength imaging in this region is huge for many different science groups, as I'll show in a moment. So in this plot here, you can see this is a plot of wavelength, of course, and this is 5 sigma point source depth. And I'm comparing CASTOR to these other facilities, and they're all marked by color. And if you can read under each passband, there's an image quality here. So this gives you some estimate of the image quality. It's not full width half max, it's E50 or 80, I believe. But you can see that we have a lot of information in the infrared thanks to the space facilities, and then we have a lot of information coming up from Rubin. LSS Canada, the CASTOR's contribution here in this landscape would be to add the space-based imaging at the short wavelengths, almost as deep. So this is the 10-year depth of the LSST survey from Rubin. So in this primary survey, the CASTOR imaging would be nearly as deep in the G band. And this is less than a 1 hour exposure. It's remarkable how deep you can go in space in point sources, even with a small facility. So it's nearly as deep in the G band. It's more than a magnitude deeper in the U band. And of course, it adds in the UV band. And it does this at space resolution. Okay, so this survey, I'm not sure how I'm doing for time, but this is a plot. Essentially, you can think of this as from a number of famous astronomical surveys. There's flux decreasing on the horizontal axis, decreasing to the right. And if you saw that, this is a parameter here, which is the total survey area divided by the image quality squared. So this is just some metric to give you an indication of the total number of resolution elements within the survey. So in this kind of a diagram, the surveys with the richest amount of information would be over to the right and at the top of the figure. And so it's not surprising you see the Euclid and LSST and W first Roman surveys up here, and CASTOR is also up in this region. Of course, the difference is it's working at shorter wavelengths. Okay, so in terms of capabilities, how does it, and I've said this several times, but let's go into a bit more detail about the scientific niches. In this era where we have ground-based optical imaging and we have lots of imaging in space resolution from the infrared telescopes. So one thing of course, is that you have the UV blue sensitivity and the good response, which is important for a number of reasons, and the angular resolution. So if we start with angular resolution, here we have in the lower left corner, this is a CFHT image, a deep image of a globular cluster in the Milky Way. This is sort of comparable to what you might expect after years of operation from LSST. And this is CASTOR. This is actually a Hubble image degraded to CASTOR resolution in the U-band. So you can see the advantage here for certain kinds of programs of having the good resolution. In the upper left corner, you can see the CASTOR passbands again. This is similar to the information presented in that discovery efficiency plot, but here it's just the total system throughput without including in the collecting areas or the field of view. So you can see that we have wavelength coverage, admittedly not the large number of filters that was available on Hubble, in broader passbands, but still a valuable complement to these future missions like Roman, as you can see on the plots on the right. So if you're interested, like me, in stellar populations and galaxies, if you're working with just Roman, for instance, for resolved stellar populations, and you want to understand the mix of stellar populations, so chemical properties and ages, it's difficult when you're focused entirely on the infrared region. So the ability in the upper plot shows a range of metallicities at fixed age and a range of ages at fixed metallicity. And so it's possible using the infrared to separate age and metallicity effects, but you can see in the lower figures that if you add in the short wavelength imaging from CASTOR, your ability to separate age and metallicity effects is greatly improved. The advantage of the Hubble, of the larger field of view, is illustrated here. If you look on this upper figure of on the left of the Andromeda galaxy, this is the individual pointings from the FAT survey, which was one of the largest of programs, large programs ever done on Hubble. You can see that many of these so-called bricks used to tile about a third of the optical extent of the galaxy. But with CASTOR, you'd be able to cover the galaxy at these short wavelengths in just 6 pointings in these 3 filters. So for, in terms of resolution, below this, you'll see an actual image of the galaxy image for the cosmos field. And this is a simulation of what CASTOR would see in a admittedly long exposure. This is a 100-hour exposure. And so this is using GalSim. So we take the actual sources, or for the brighter objects, and then for the faint objects undetected by GalX, we use some simulations and then propagate the expected light, the SEDs, through the telescope and onto the detector to get a simulated view of what GalX would see in this 100-hour exposure. So the benefits of the angular resolution are clear here. And then one thing else I will mention is, we're living through a very interesting time in astronomy with Gaia. So astrometry has never been sort of more exciting and produced more interesting results. But Gaia only extends to about 20th magnitude. And so LSST will be able to push astrometric studies beyond Gaia to fainter limits, which is very exciting. CASTOR could also do this. And indeed, because of this point source sensitivity, the good image quality and the small pixels, you could work, be able to extend the sort of build on the Gaia astrometric results to do some quite interesting science, particularly in the Milky Way. Of course, Roman should also be included in this plot. I haven't done that, but it's totally fair to include Roman in here as well, because it will be equally powerful for astrometric studies. Okay, check the time. All right, so I have one slide from each of the science working groups. I think I don't want to spend too much time on this. I know we can perhaps have questions on various science topics afterwards or discussions, but I wanted to maybe choose a select number of these to sort of highlight the breadth of the science case. So I'll start off with cosmology, because CASTOR was always, going back to the original concept study, it was envisioned as making some type of contribution to cosmology and dark energy studies. So I'll begin with just reminding you that all these so-called stage 4 dark energy experiments are designed to combine wide field, high spatial resolution, broad wavelength coverage, and high cadence to constrain dark energy. And that no single experiment perfectly satisfies all of these criteria. So it's really the facilities working in tandem that are going to be most powerful for understanding dark energy. CASTOR's role in this, first and foremost, is from the short wavelength coverage, and particularly for the photometric redshifts. So adding the short wavelength coverage improves the photometric redshifts. You can see this in the plots at the bottom of this panel. So if we start off with just, this is from a paper by Melissa Graham that was published last year. So what Melissa did was basically the standard approach of taking galaxies at known redshift and then simulating with different photometric surveys how well you recover how well the photometric redshift recovers the true redshift. And so in a perfect world, this would be a perfectly thin line with no scatter and no outliers. Of course, that's difficult to achieve. And if you just use the optical data from LSST, you can see there are a number of outliers, problem redshifts, and there's quite a lot of scatter here. If you add in the Euclid infrared data and then the W1 or Roman infrared data, which is deeper still, and then finally add in the CASTOR data, you get the best possible measurement of the photometric redshifts, which is probably no surprise. And so this final plot over here on the right, this is combining the CASTOR imaging at the shorter wavelengths with the deep LSST imaging at the intermediate wavelengths with the very deep infrared imaging from W1 Roman. And this is some quantitative measurements from Melissa's paper on how the standard deviation decreases with as a function of different data sets used in the analysis and also the fraction of outliers. So beyond that, for cosmology, CASTOR would also allow object detection and deblending at short wavelengths, which is going to be an issue for people who've worked at very deep imaging from the ground. Understand that often understanding the nature of the sources in ground-based resolution at the detection limit can be quite tricky. So if you have improved resolution in the same passbands, for instance, in the G band, from LSST, the deep imaging from the ground, and you have the sharper imaging from space in that same bandpass, this is very valuable for understanding blending, color mixing, and object detection. And then finally, I would note that Euclid and all of these facilities are intending to make shape measurements for weak lensing. And the addition of yet another facility to make shape measurements at a different wavelength can be very valuable potentially for understanding systematics in the measurements, which are crucial. Okay, so moving right along, I wanted to say something about time domain, because when we originally came up with the CASTOR concept a number of years ago, this did not even feature in the science case. But of course, now time domain astronomy is a burgeoning field. There's all kinds of interesting things going on, and we expect this to continue in the next decade. So the science working group doing time domain astrophysics identified a couple of potential programs. One is the so-called target of opportunity observations for multi-messenger events. So CASTOR is primarily a survey instrument, but it does have a guest observer mode, and it can be used to follow up particularly interesting events. Of course, not all events would be accessible at every point in time, but for a subset of events, if it falls in the right part of the sky at that time of the year, then it's possible to easily slew to the object of interest and do follow-up observations. So for multi-messenger events, if you're looking for electromagnetic counterparts to some gravitational wave events, for instance, some of these can be quite interesting. Now, they have to be localized, and the UV is a particularly important region of the spectrum for understanding the nature of the progenitor and the details of the explosion mechanism. It's important to get on it quickly because the short wavelength light fades quite rapidly. Now, CASTOR's role wouldn't be to localize these events. There are surely going to be other smaller facilities that will do this, probably at ultraviolet wavelengths. I know a number of these that are in development. I don't know if any has been formally approved yet, but one of them or multiple such facilities will be approved. And so they will be able to localize the events quickly. And then CASTOR would be able to follow that up. And the advantage is you have the relatively large mirror, good UV sensitivity with angular resolution, and you have imaging and spectroscopic modes. So for a subset of these, there's an opportunity here to do some interesting work in the time domain astrophysics. There was also a second proposed legacy survey, which was to monitor 2 of LSST's 10 square degrees deep drilling fields for a number of different science reasons, but basically for adding in the UV component to that monitoring campaign. Well, I've already mentioned some of the galaxy science. I talked about the CASTOR simulation of the cosmos field. Spatially resolved star formation histories is another obvious thing that you would do, basically to map the star formation rate and stellar populations within large numbers of galaxies at Hubble resolution. So that's another candidate science program, something that could be, would be done with the CASTOR primary survey. The AGN and and supermassive black hole science working group devised a reverberation mapping campaign. Reverberation mapping is often it's well done in the ultraviolet region because the emission from the inner the region surrounding the AGN is basically dominated. The flux is emitted primarily in the UV region. So they devised a reverberation mapping campaign which would spend months looking at a region of 12.5 square degrees. And they would do this with both imaging and slitless spectroscopy. And so this would allow black hole mass measurements for a large sample of AGNs over a wide wavelength range, which is apparently a relatively unexplored part of parameter space. Okay, so for near field cosmology, there are a number of interesting things that you would like to do. I showed earlier the advantages of adding in the short wavelength data to imaging at longer wavelengths from Roman or other facilities. So it is very interesting for as we try to understand the structure and stellar populations of low mass systems in the nearby universe. It would be very powerful. And particularly, I like the idea of using multi-epoch imaging to do proper motion measurement studies of individual objects and streams in the galactic halo, which is very interesting for a number of different science regions. Now, one of the other candidate legacy surveys that was identified was the Nearby Galaxies survey, which would target about 300 galaxies within the local volume. You can think of this as the sort of CASTOR analog of the very successful Nearby Galaxies survey that was done by Galax. So, of course, the advantage here is you have a huge improvement over Galax in angular resolution and much better aerial coverage than Hubble. So I think there's really a lot of potential there. In terms of stellar astrophysics, there's many things you can do with white dwarfs. With the broadband photometry, you can identify objects through the various means to look things that appear to be metal poor and follow up those potentially interesting objects. You could measure the structure of the Milky Way from blue horizontal branch stars. In fact, you could even do this in Andromeda if you wanted to. And there's interesting things you can do with white dwarf populations in star clusters, including globular clusters. For exoplanets, extrasolar planets, I didn't really go into this in great detail. Of course, there are certain things that you could do with the wide field imaging mode. You could do monitoring campaigns in dense environments, such as omega and other globular clusters, or perhaps bulge fields. But I didn't really mention this in much detail, but there's a plan is to have a single chip with a transmissive diffuser plate to basically produce a fat PSF, but with very precise photometric measurements that could be used to observe brighter objects, so exoplanet host stars, and to do transit spectroscopy and phase curve studies to understand basically the atmospheres in these exoplanets. So condensates in the atmosphere, and understanding basically the structure and composition and the temperature and pressure structure of the atmospheres in these exoplanets. So this again is some of this work is underway with the Hubble Space Telescope, but in the future, Hubble may not exist, and so this short wavelength information could be potentially very valuable to complement the long wavelength information to better understand exoplanet atmospheres. And then finally, for small bodies in the solar system, there's a number of quite interesting projects that were proposed, including using the primary survey. There's multiple exposures, and over a 10-minute period, for instance, you can see the objects at the outer region of the solar system moving in over 10-minute timescales. So you could detect objects in interesting parts of parameter space, given that CASTOR's point source sensitivity is high compared to a single visit with LSSE, for instance. You can find fainter objects, and so that means understanding the structure of the Kuiper belt for massive objects at greater distance or less massive objects nearer in. You can also use the imaging to characterize the binary fraction in the outer solar system, which is interesting for constraining models of the formation of the outer solar system. And by adding in the UV measurements and the U and the G measurements to longer wavelength observations from other facilities, you begin to get a handle on the chemical composition of on the surface of these remote small bodies in the outer solar system. Okay, so wrapping up. So where are we at the moment? So there's one study underway, which is notable, and another one about to start. So in May, the CSA started a new study called a Space Technology Development Program Study, which is designed to retire risk in 5 critical areas. So the areas I've listed here are the telescope optical mechanical design, the detectors and large focal plane development, the fine steering mirror, this UV spectrograph for doing the parallel instrument, and also the precision photometer, which was really more at the notional stage, and so it needed to be have a proper design. So that work started in May and is underway, including some of it in collaboration with our partners, including JPL. Now there's a second study, a phase 0 study, which is going to begin in October. The request for proposals just came out 10 days ago. So proposals are being written, and this is going to deal with updating the science case, coming up with a full detailed science plan, etc., maturing the technology and getting everything ready to proceed with construction. And this is going to be carried out with our prospective partners. Hopefully that's the intent. And with luck, we could launch as early as 2027. And so I know that's an international audience, but given that the UV Club was hosted at Caltech in the US, I wanted to say a few things. So we basically, CASTOR, the development up to this stage has benefited from having international partners. There's quite a number on the last science report. There were over 100 scientists, and a good number of them were from other countries other than Canada. JPL, I would like to call out in particular because they've been very important in moving the concept along. And the hope would be that the US community can join. JPL could lead participation of the US in the mission, perhaps by building the cameras for the facility. And I think this would be in the interest of CASTOR and the US community. The technology is the world-leading technology resides at JPL. In delta doping and enhancing the performance of these detectors at the shortest wavelength region, which is crucial for the mission and for many of the science cases. And the US has a long history in UV astronomy, of course. The other thing I'll remark is Hubble has a finite lifetime. We got a scary reminder of this last month when Hubble stopped working. It's now back after a month hiatus, so that's great. But again, it is a reminder that the Hubble does not have an unlimited timeline. So it will be important to ensure that access to the shortwave region is maintained over the next decade, particularly when we have these new facilities coming online in the infrared, given the richness of sort of wavelength and scientific heritage. So I will stop there, and happy to take questions or have a discussion. I'll just let this movie run as we do that, which was a movie that we produced during the most recent study. So thank you.
Okay, wonderful. Thanks for that comprehensive review and story of CASTOR. So it's time for questions. Please raise the hand, and after your question has been answered, lower it. Raising the hand, I think that facility is under reactions. Okay. Give it a minute. Ilaria.
Yeah, I have a question about the design of the filters. It's more of a curiosity. So what drove this choice of this broadband only 3 filters? Was that just to go for simplicity, or was that for the science? You just wanted to maximize throughput, and so that's why the wideband?
Both, as a matter of fact. As I said, when the original concept was devised, we were well aware that Euclid and WFIRST were going to be making measurements where photometric redshifts were absolutely crucial. And so it was clear that you needed to produce the short wavelength broadband measurements. And so that was part of the decision, but in the end, we decided that, you could do a tremendous amount of science with just these 3 filters. And if keeping the simple design where there's no moving components, etc., you're able to do, as I hope I demonstrated here, a huge amount of science. If you add in multiple filters and filter wheels, etc., the complexity and the risk of the mission and the cost of the mission goes up. So this was perceived to be a compromise. Now, having said that, when I give this talk, a frequent question is, it would be great if you were able to split up the UV band, right? So we understand this. And so in the phase 0 study that's about to start, that's something that we could certainly consider. So for certain programs, if you had a filter wheel in just the UV channel, for instance, then yes, that's going to be a trade study that we're going to do during the phase 0 study.
Thank you.
Mike, go ahead.
I had to unmute yours. Yeah, thank you for the talk. I'm interested especially in the low-res spectroscopy. And I noticed that a lot of your ray traces had quite a few bounces, which probably will lower the throughput a bit. So are there still ongoing discussions on raising the throughput in the far UV spectra?
You're talking about the GRISM mode?
Probably the GRISM mode, but you had another mode, I believe, too.
Yeah, so there's 2 modes. One is basically you slide in a GRISM, and then you disperse the spectra in the UV and U band. We decided that in the G band, there was no sense in doing this because you're competing against the ground facility, so it didn't make sense. But yeah, so you'd have a low resolution of on the order of a few hundred in the UV and the U band. So that's one mode. But I wouldn't say it's just significantly, I mean, of course, we're always mindful that we want to keep the throughput as high as possible, but I don't think that the throughput is necessarily going to be low in that particular mode. Now, there's a, sorry, the screen is blocked. There's also a UV, small UV spectrometer, which is based on a DMD, a digital micromirror device. These have not been flown in space yet, but they've been explored for the Euclid mission, and they've been built for ground-based facilities. So this is one of the things that we want to look into. So this would do two-dimensional spectroscopy in the UV region from so the full UV band from 150 up to 300 nanometers at a resolution of somewhere between 1 and 2000. And of course, it's configurable. So you could do a single object, or you could do multiple objects at one time. So that is still very much, so our partners in India are quite interested in this, and they've been doing work in the lab and in design to sort of mature that possibility, because it would be something that they would like to contribute to the joint mission. I don't know whether it's what the throughput is, whether it's not competitive or not, but is there a particular science program where you think we might be UV or throughput challenged for UV spectroscopy?
Well, I'm most familiar with FUSE and Hubble costs, and I think it would be competitive with the G140L on costs.
Mm-hmm.
But faint object spectroscopy, quasars, hot stars, white dwarfs, those would be the areas that you'd like to see quite a few more sensitive observations, especially if Hubble goes away.
Yeah, no, definitely. And I do agree. So one of the things is that in the science case for the facility, which is voluminous, is really heavily weighted to imaging at this point. And so everybody on the science team will agree that the spectroscopy is valuable. And we have some science cases with differing levels of detail, but it does need to be matured. And yeah, I take your point that the highest throughput you can get is very valuable.
Thank you.
Okay, Amit.
Hello, sir. Thank you for the talk. And my question was, are there any new information on the time domain astronomy that the CASTOR program is going to take part in? Like any particular regions that the survey is interested in looking into high cadence?
I see. So you're talking about the monitoring campaigns. Has there been any development in the last 2 years on specific details for the monitoring campaigns?
Not exactly, but high cadence photometric surveys for quite some time.
Yeah. So again, so all of the science cases that I mentioned so far are sort of candidate surveys. Nothing has been finalized, and we expect that in this phase 0 study, which is going to start in October and run for a year and a half roughly, those are the sort of issues that we should settle at that time. So for instance, monitoring of LSST deep drilling fields. Well, I mean, one thing that we can do is get the actual cadence and the depth and the choice of specific fields finalized during that time. There are programs, for instance, of monitoring star clusters, et cetera. Well, we should decide on what those specific clusters are. Yeah, so at this point, we have the concepts of basic ideas of what kinds of programs look like they're appealing for programs, but nothing formalized in terms of this is an object that we're going to be observing, and we're going to observe it with this cadence and depth.
Thank you, sir. Thank you.
Yeah, Harvey.
Hey, Pat, thanks for that. Could you just be clear about what the CSA contribution is at this stage to the project, and looking into the future, what do you think their contributions are likely to be? I know this is crystal ball gazing a little bit, but it's the kind of thing you have to do with a project like this, I think.
So when you say CSA contributions, can you be more specific? What do you mean?
Well, I mean, how much financial backing are they likely to give to this project, for example?
Okay. So the answer to that is that so the CSA budget does not, there is no sort of A-based budget for the space agency that is capable of funding a mission of this scale. So, but that is true of most large astronomy projects in Canada, as you know well, Harvey. And for instance, the example would be the James Webb Space Telescope for space astronomy. That was approved as a request to the government. And it was funded by the government, gave the money to the space agency, roughly the same amount of money involved in this particular case, by the way. So at the moment, the CSA has all the funding in place to continue with the technical studies and the phase 0 study up until the middle of 2023. At that point, we hope to have government approval secured, in which case funding will be made available for this particular project.
So this would not be out of the CSA budget. This would be a contribution directly from the government of some sort.
Exactly.
Okay. Thanks, Pat.
Yeah.
Okay, other questions?
If I can just quickly follow up on that, like, are you looking for contributions from other countries? I know you mentioned the US, but maybe also Europe.
Yes, I mean, we're always looking for potential. I mean, I would say there's quite a lot of interest from different countries. At the moment, we have to present a sort of a partnership scenario to the government that we expect to be doing that in the next year or so. So if there's a hardware component in particular for the mission that another country could contribute, then we're definitely interested in collaborating. Now would be the time as well, right? Because the phase 0 is about to start.
Okay, Wenbin?
I'm curious about the dichroic glass. Is that enough to separate cleanly the light in different bands? I know in filters you can filter out all the photons that are not in the particular band. Is the dichroic so good that it can no optical leaks in the UV?
Yeah, so that's a very good question, and we're very mindful of the red leak, right? Is what you're getting at. So yes, and so we have a requirement that the suppression has to be at the sort of 10 to the -4 level. At the moment, we definitely well below that for the G band and the U band. The UV band is a bit of a challenge. We're a little better than with 3 on Hubble, but as you know, for certain astronomical sources, like very hot sources, for instance, you can have a red leak problem. So at the moment, we're sort of right on the edge of what we consider to be an acceptable amount of red leak. And we tend to sort of continue to look at this with the dichroics and the coatings. If it isn't possible to meet the spec, then you can of course add in a single filter, one more optical element. You pay the penalty that there's a reduced throughput, but as you said, you can filter out the long wavelength light with that additional component.
Is there anything you can do on the detector, on the CMOS side?
Yeah, you can. In fact, that's so JPL, who are experts in this, they're going to be, as part of the technology work that's underway right now, they are going to be doing delta doping of detectors, candidate detectors, and also doing coating of the detectors to help define the passbands. So you can do that, but yeah, it's a question of you need a suppression of about 1 part in 10,000. So it is challenging.
Thanks.
Yeah.
Okay, there's a Kulkarni at Desi.
Thank you. I have one technical question related to the low Earth orbit. In low Earth orbit, the atomic oxygen is concentration is high. Is it affect your mission for measurement degradation of the observation? Did you thought about this?
Yeah, we haven't thought about it so much. I mean, what you say is correct. I mean, what I would say is that Galax was in a lower orbit than we were. Hubble is in a lower orbit than we are.
Okay. Yeah, because especially silicon detectors are affected a lot. Yeah, so they degrade very fastly when atomic oxygen is yes, as acts like a dopant, and okay, it creates some defects, and yeah, that's okay. Thank you.
Okay, thanks.
Okay, any other questions? So, Kareem.
Thanks for the talk. I was interested in the improvement of astrometry at the faint end compared to LSST and Gaia, which looked pretty cool. But I was wondering, I would have thought that most objects that are too faint for LSST would also be far enough away that their parallaxes would be smaller than you can measure with sort of milliarc second astrometry, or would be really red, such that a blue mission, in a blue mission they're hard to detect. Is there a sweet spot where the improvement helps the most, or is?
Yeah, I should say that the plot I showed you there a while ago was it's a very naive thing, right? It was where you take, for an imaging detector, you basically parameterize your positional error as some systematic plus the ability to sort of localize on a source given the size of the source, the pixel sampling, and the signal to noise ratio. So you're right that so something more sophisticated really should be done than what I've done here. But I think the point stands, right? That you, with the small pixels, so the question is, are there sources below 24th magnitude, which are still have beyond the detection of a single visit of LSST, for instance, that are still going to have a measurement, a positional or a proper motion measurement? I suspect that there are, given the population of many different varieties of stars in the galaxies. And I would say the CASTORs, I mean, it's not, for probably most of this work, the G band would be the preferred band, right? So it's not really in the blue, it's sort of more in the green part of the spectrum.
Right, that makes sense. Yeah, I imagine for proper motion, there's quite a bit to do. I was thinking more for parallaxes, where it's probably harder.
Yeah, agreed.
Thanks.
Yeah, I don't think CASTOR is well suited to doing parallax because when you make those measurements, you always anti-sun, and to do parallax, you have to get it around the year. So you'll always be doing it the same solar longitude, if I'm not mistaken.
I see.
So you may have the precision, but you won't have the sensitivity to make a parallax. Anyway, so other questions? I would not immediately discount, Pat, the CASTOR the proper motion, which of course grows with time, compared to LSST, because at the sub-milliarc second level, the ground is a terrible place to do. Well, it's a terrible place to do astronomy, but at the sub-milliarc second, it's a really terrible place to do astronomy. The differential chromatic refraction modeling has to be done very, very well. And I don't know whether those LSST plots are, you take the full width half max, divide by signal to noise ratio, and then divide by 10 years. If it is something like that, I would hardly believe that.
Yeah.
On the other hand, if someone has actually thought through the whole thing and done a real simulation, I would buy into that.
Yeah.
There's a huge advantage of being in space.
Yeah, I agree. I agree with that. And in fact, these plots are these sort of simple-minded plots.
Yeah.
So
So
it's something that cries out for deeper analysis during the
right.
phase.
And and history is on my side. There are many attempts on ground to do proper motion and so on. In proper motion, unlike other things, if you get one proper motion wrong or one parallax wrong, no one believes your remaining 99 of them. So the ground-based stuff, has a certain nominal sensitivity, which is, I would call, the naive sensitivity. And then there are always pathological exclusion things which destroy that. If you have, for example, a double star with a red and a blue companion, you will get actually centroid shifts. The DCR will be different for the two. And so actually, I would have your team study and even go out with a very bold statement like, yeah, LSST may be big and so on, but we can do better. But then, of course, you have to do your planning for that. You have to increase your you have to become more relaxed about your anti-sun pointing.
Mhm.
I had a couple of other questions since we do seem to have some time. If Canada were to build this whole mission and operate, what is your estimate cost?
Cost is about, latest cost estimate is about $450 million Canadian.
Okay, so that's like start to end.
Yep.
Okay, that's like what, $20 per Canadians or something. So is that something Canada can't do on its own?
I think, I mean, so for instance, the RadarSat Constellation mission, which was basically 3 satellites roughly the size of CASTOR, that was launched in June of 2019. That was a much more expensive mission. But I would say the likelihood of Canada proceeding with the mission is increased if there are partners involved. So I think that the hope would be Canada would lead the mission, and certainly there's a history. There's some track record here in that the James Webb Space Telescope, our contribution to that, although small to the total cost of James Webb, which is a very expensive mission, of course, is roughly the same size as CASTOR, the Canadian fraction of CASTOR. So this is why a partnership with different countries like JPL, who has expressed an interest in building the camera, and they have the expertise in this technology, that would be a significant contribution to the mission. And India, which has a satellite, has a rocket and has a satellite bus, and has interest in some aspects of the instrumentation, such as the spectrograph. Sort of all the components are there for a nice mission at a cost point that is roughly the same as Canada's contribution to James Webb.
Okay. Has someone looked into the glow from the oxygen line in the, I forget, there's a fairly bright air glow at 2471, maybe? It's right in the middle.
Yeah, I mean, there's very little you can do about it, of course. We did consider the possibility of changing the pass bands in the ultraviolet region to miss that line, because a significant fraction of the sky brightness comes from that single line. But in the end, we've decided that it's very difficult to accommodate that, and so we'll just live with the fact that there is a bright emission line.
Yeah. So I had a question. It's really not very advantageous to launch a UV mission in low Earth. I mean, this has been, unless you're really running out of money or some totally desperate situation, but this is a big mission. Why haven't you considered at the very least, geosynchronous orbit?
Yes, I mean, we have considered it. There is a cost factor, right? We're mindful of the cost. India, the ISRO has a rocket, a GSLV, which can reach geosynchronous orbit. geostationary orbit. So it's something that we have considered, but at the moment we think that the trade with low Earth orbit it's acceptable to be operating at 800 kilometers. After all, Galax observed there to great success.
Well, I don't think so. I really think you should review this more carefully. First of all, the rocket launch the costs have come down. Especially the entry of this private sector in the US, it's going to put a lot of pressure on other vendors anyway. I really think you should look into something like, at the very least, geosynchronous. Doesn't have to be at an inclination of 0. Even an inclined one is fine, because there are issues. You can't compete with people in the genuine, equatorial geosync. But the gain you have on a uniform, a very reliable background, much darker sky, okay, is enormous. Of course, the one thing you'll expose yourself would be to more radiation damage, but you're using CMOS anyway, so it's not. They're more robust than CCDs.
Yeah.
And the launch cost is not going to be the big, thing that breaks the back of this $440 million project.
Yeah, no, it's a good point. It's certainly something that we're going to revisit with phase 0. Well,
and also your pointing constraints are extremely high at this point. Okay, you're in a sun synchronous orbit. You can't point close. You have very strong. I don't know what your Earth limb angles are. So if you want to do, and then your ability to react to TOO is almost, you're completely at the mercy of, it's not like these EMGW events happen every second or something. You can, the sky that is accessible with the current system is extremely tiny. My guess is the fraction of the sky you can do, bearing into account of increased background. I'm not worried about your batteries and so on. I'll assume you have infinite battery, but I am worried about constraints such as you can't obviously have a thing to Earth's limb. At 800 kilometers, Earth is very, very big in your sky. So if you want to do the whole EMGW or any TOO, which is not so restrictive, you really want to be in a higher orbit. You don't want the oxygen line. It's a shame to build such a big mission with 9 milliarcsecond pixels and then suffer oxygen line. I mean, that somehow seems to me very wrong. So I can see one thing you'll say, oh no, but your telemetry or your downlink will go up a lot because you're probably transmitting, I forget, maybe a megabyte per second, because you're dumping your pixel every 600 seconds. And that is an issue. But again, with the new Ka band, there's tremendous increase in the downlink speed.
Yeah, and we are in fact baselining to an high-speed optical downlink. And I agree with much of what you say, Shri. The problem is you have to be mindful of mission creep, right? I mean, whether you want to build the telescopes to be predominantly optimized for time domain astronomy, or whether you want to do mostly survey operations and accept the fact that not every object will be accessible.
Well, but even if you want to do, okay, you can. I'm thinking of CASTOR. It does the first, the deep sky, and then it turns out that LSST is really not doing all that well in astrometry. Okay, because I don't know. Again, I could be wrong. Maybe someone has done a deep study, but I would say no. If I want to do astrometry, I'll never do it from ground. I'll do it in space, or I'll do it with radio or something, but not optical. Yeah, then you want to have a 10-year mission, extend this mission, and you want that baseline, and then you want to observe, proper motion is fine, but parallax is wonderful. So at that point, you really want to have the 6-month ability to see, observe at different solar elongation, solar longitude. So it becomes and there is no other mission that is really going beyond Gaia right now.
Yeah.
Okay, well, we're approaching the time of so if I would say it's time to sign off. Thanks again, Pat.
My pleasure.
Okay.
Thank you very much. I'll stop recording now.